So in this section, we're going to be looking at the acceleration vector in more detail. First, it's going to relate back to breaking acceleration down into its normal and tangential components. And so these are two ideas that we've seen a lot in this last couple sections, is the idea of the normal and tangential unit vectors, right? We studied the normal unit vector, which was n hat, and the tangential unit vector, which is t hat. And so we've looked a lot about what they tell us. The tangential one is telling us about the direction it's going. It's pointing in the direction of velocity. And then the normal one is orthogonal to it, and it points in the direction that the curve is turning. And so we can use those to our advantage to help better understand how acceleration is acting on a particle moving through that curve. And this is not a new concept. So it's not... which is good. We've seen this a lot in physics before, so if you've ever taken a physics class, so in physics, it's typically helpful to break up force vectors into their components. And right, what that looks like is if we have some particle like this, and there's a force acting on it, we might have some force vector. Then if we wanted to study how that force acted on the particle, the first thing we would do is superimpose a coordinate system onto this situation, and typically it's a standard step to break down the force into its x and y components. So here we would have the x component of force, and then this would be the y component of the force. And so that could tell us how the force is going to move this particle. And so that's breaking it up onto the global coordinate system, the x and y axes. But what we've been developing over these last two sections is a local coordinate system at every point on a curve that we call the TNB frame. And so you can see that right here. I have a little example curve through space r of t, and then we're specifically looking at this point on the curve. So this could be t equals some specific t value. And it has its tangential and normal components. And so if I were to just draw an example acceleration vector, it might look something like this. So that might be the acceleration of the particle at any given point. And so acceleration can cause both an increase in speed, that's the kind of the version we're normally used to, or the context we're normally used to thinking about acceleration in, is a change in speed. But it can also cause a change in direction. Right, so a change in direction. And that is also from physics. If you remember studying uniform circular motion, then a acceleration pointing towards the center of a circle, instead of causing an increase in speed, causes the velocity vector to change directions. It's a force causing a change in the direction of the velocity vector. And often this is happening at the same time. There's both an increase in speed and a change in direction. So if we were interested in how much of the acceleration vector A is changing the speed of a particle on this curve, then we want to know how much of the acceleration vector is pushing in the direction of the curve. Or in other words, it's how much of A is in the tangential direction. So this is the amount of A in the tangential direction. And you might be able to come up with the formula for this. We'll call that A sub t. And if this is the component of acceleration causing a change in speed, then that's just going to be the derivative of velocity, or of the magnitude of velocity. So that's the change in speed as t increases. And so what that would look like here in our diagram is the amount of this acceleration vector of the particle that's causing it to change its speed, in this case increase its speed, is going to be the amount in the t direction. So that would be this component of acceleration. That's what we call a sub t. And in that case, it's equal to, the first derivative of speed. So that's that component of acceleration. And now if we wanted to study how much of the acceleration vector is causing a change in direction, right, that means, in other words, that could be called a change in the direction of the velocity, or the unit tangent vector. Both of them are the same. They both have the same direction. Then that is going to be the amount of acceleration in the normal direction. So that's amount in the normal direction. And that is equal to, well, if you take a look at the diagram, the way we can find the amount in the normal direction is if we know the acceleration and we know how much is in the tangential direction, then this forms, it will always form a right triangle, and we can just use a version of the Pythagorean theorem to construct the other leg of that right triangle. So that is just going to be the square root of the length of the hypotenuse, which is the length of the acceleration vector, squared minus the amount in the tangential direction, squared. So that's just an application of the Pythagorean theorem, because breaking down these forces into two orthogonal vectors is always going to form that right triangle. And so an example of a curve that might have acceleration in the normal direction but not in the tangential direction would be if you were traveling around a circle at constant speed, right? That would have acceleration always pointing towards the center of the circle, orthogonal to its velocity, and there would never be any component in the tangential direction if your speed is uniform around the circle. So now that we have these two forms or components of acceleration, we can write the entire acceleration vector in its component form. And the way we write that is acceleration, the whole acceleration vector is equal to the amount of a in the t direction times the unit tangent vector plus the amount of a in the normal direction times the unit normal vector, right? And that's kind of the same form that we usually write vectors in. There's a some vector might be equal to some magnitude in the I direction plus some magnitude in the j direction. But in this case, instead of using that global coordinate system with I and j, we're instead using a local coordinate system where our I hats and our j hats become the unit tangent vector and the unit normal vector with some magnitude attached to it, the amount in each direction. And as a note, the acceleration will always lie in a plane. So if you notice, let me make a note here. So notice the b vector from the t and b frame does not show up in A. So there's never going to be a component of A in the B direction, because just as a property of acceleration, acceleration always lies in the t and in plane. It's always going to be in the plane spanned by those two vectors. And do you remember we have a name for that plane that's called the osculating plane? And so that's true even if our curve R of t has 3 components. So it's even if our curve has 3 components. Right, so even if the curve has an I, J, and a K components to it. So it'll always be in the oscillating plane. And that's why we study those planes formed by the unit normal or the unit normal vectors, or the unit the principal unit vectors, right? T, N, and B. So let's take a look at 2 examples that will kind of show how we use the components of acceleration. So here in example 1, we're asked to write the acceleration vector in component form at the given value of t. So here's our curve R of t that we're looking at. This is the position function. And now we're going to find its acceleration at the point t equals 1, broken up into its components. And so all we have to do is we have to find the magnitudes of at and an, and then just tack them on to the unit tangent vector and the unit normal vector. We don't actually have to solve for these. Those are just the directions. So we really are just looking for these magnitudes. So first we'll start by looking for the acceleration in the tangent direction. So we'll first start by finding the derivative of the speed function. So first we'll find at. And so that's going to be the derivative of speed. So let's first find what that velocity function is. That's just going to be I plus 2j plus 2tk. And the magnitude of that will be the square root of 1 squared plus 2 squared plus 2t squared, which will equal, that becomes 5 plus 4t squared. So there's our speed function, and now we'll take its derivative. So dt, dt of speed is going to be the derivative of that square root function, which will be 1/2 times 5 plus 4t squared to the negative 1/2 power rule, and then chain rule will be times 8t. So that is the amount in the tangential direction. So let's evaluate it at the specific value of t, which was t equal 1. So let's do a sub t evaluated at 1 is going to be plugging 1 into this, which ends up giving us 1/2. 5 plus 4 to the negative 1/2. How do I do this? Negative 1/2 times just 8. And what does that simplify down to? So 8 divided by 2 is going to be 4 times the square root of 9 in the denominator, which gives us 4/3. So 4/3 is the amount of acceleration in the tangential direction. And now we'll use that to find the amount in the normal direction. So now we'll work on constructing a sub n. And right, that's equal to the square root of the magnitude of acceleration squared minus the amount in the tangential direction squared. So we first need to find what the acceleration vector is and take its magnitude. So acceleration is just going to be the derivative of our velocity function, which is 2k. And now we'll evaluate that, or now we'll take its magnitude. So the magnitude of acceleration is just equal to the square root of 2 squared. So that's just 2. So now we have all the pieces we need to find an. So an is equal to the square root of the magnitude of acceleration squared, so that's 2 squared, minus the amount in the tangential direction squared. So that's minus what we found earlier, 4/3 squared, which becomes 4 minus 16/3, or the square root of 4 minus 16/3, which becomes 20/9. So that's the amount in the normal direction. And so now we can take these two and write acceleration in component form. So now we know that acceleration evaluated at t equals 1 is equal to 4/3 in the tangential direction plus the square root of 20/9 in the normal direction. And so this is really great because we don't actually have to find the specific tangential or the unit tangent and unit normal vectors. We just need to put those on as the directions, the direction vectors. So now here in example 2, we're asked more of a conceptual question, and it's asking us if the speedometer on a car reads a steady 35 miles per hour, can the car be accelerating? So this steady 35 miles per hour means the speed is not changing. So another way to write that mathematically would be the derivative of speed is equal to 0. So there's no tangent component. And so when you first read this question without analyzing it, your gut reaction might be to say there's no acceleration because its speed isn't changing, or there's no change in speed, no acceleration. But that neglects that there's another component to acceleration that doesn't actually cause a change in speed, but rather causes a change in direction. So it tells us nothing about acceleration, except for the fact that there's no tangential component. So there can still exist a normal component of acceleration if the curve is turning. And so an example of that would be, like I mentioned earlier, uniform circular motion. Let me draw a little picture. I didn't like that. So here's our an example R of t. Here's a path we're taking, and if we're going in this direction, we might evaluate at this point here. And the conditions I'll set on this is that it's uniform circular motion where the speed is constant. So on R of t, let's say speed is constant. So if I were to sketch out the tangential and normal unit vectors, you might have, here's t, and here's n. Then if speed is constant, then there's going to be no acceleration component in the tangential direction. But at every given point of t, there is, t is pointing in a new direction, right? The velocity is constantly changing, even though its magnitude isn't. So because the direction of velocity is changing, there is some acceleration causing that change in velocity. So we know that all of acceleration is in the normal direction. So if I were to sketch the acceleration vector for this example, it would probably look something like that.